Hi there, welcome back to the formulaic approach. Now in this video, I'm going to be teaching you about elasticity, under which we are going to be studying Hooke's law. Now elasticity is one of the fundamental properties of solids. So, and you know solids are basically both metallic and non-metallic solids, right? Generally, solids have the following properties. First, metallic solids show the following properties. Number one is malleability. Now, what is malleability? That's the ability of solids to be hammered into thin sheets like this book or as flat as this. So we can hammer metals into thin flat sheets like this. And the second one is ductility. Another property that they show is ductility. Ductility. Now, what's ductility? Metals are ductile. Ductility means they're able to be stretched into thin wires like this. Exactly. So that's ductility. Ductility. All right. And this one is specific to metals. Okay. Another one is sonorous. Okay. Sonorosity. They are sonorous. That is, they give off music notes when you musical sound, or note. Okay, we say notes because they sound at different notes, and that's why we use them for making musical instruments as well. All right, so the point is they give off musical notes when they are sounded, when they are beaten. For example, I'm gonna beat a metal now, you hear a sound. You understand? So it sounded down, and that is a musical note. So that is sonorosity. Another property that solids now show, but is not specific to metals now, is brittleness. Now, this one is specific, in fact, to non-metallic solids, especially glasses, ceramic materials, exactly, ceramics. So you notice our glasswares at home, when you drop them on the floor or on hard objects, they break easily. So this is the ability of substance to shatter on impact with a solid material. So that is with another solid material. So that is brittleness for solids. Now another thing they also show, as we have seen before, if you have not seen my video, check it out, on expansion in liquid, is that solids actually expand as well. Solids also undergo what? Expansion. Solids undergo expansion. Now, this expansion is going to be viewed in two perspectives. The one that has to do with temperature, and the one that is having to do with their innate ability to be stretched. And that one will be called elasticity. Elasticity. By the end of this video, make sure you stick till the end. I'm going to show you the link between this elasticity and the expansion that I have done in linear expansivity. All right, let's begin now. So what is elasticity? Elasticity is the ability of a solid to return to its original position after it has been stretched or after it has undergone deformation under a particular stressor. And that stressor is usually a force or a load or any or an effort that is put into stretching it. Exactly. So basically, elasticity is the ability of a material, of an elastic material. So it's the ability of an elastic material to return to its original shape or form or position after it has undergone deformation under a stress, deformation under a force. Exactly. So forces cause materials to get deformed. Exactly. Forces cause materials to get deformed. Madimi, I had a rubber band here. I'm going to show you. If I stretch a rubber band, you're going to see the rubber band elast. Is that okay? It's going to elast. And after a while, it will stop elasting. That's what we are going to be seeing under Hooke's law. Exactly. So basically, that is what elasticity is. Now, we typically use a spring, okay? A spring in our context for explanation and or an elastic string. Exactly. We use a spring. A spring is naturally elastic. That's why it's called a spring or an elastic string. Exactly. So I'm going to be using a string. For example, if I attach a string to this point, to a fixed point here, I attach a string like this. Let's say it's in its resting position like this. This is resting position. And let's put it upside down like this. So it is fixed upward here. It is fixed here. It is fixed here. And here is our string. Then a load is now attached to it. If I attach a load to it, this thing is going to stretch. It will stretch to about this distance. Just this one load. Stretch it from this distance. This is its natural height. This is the natural height of the string. But the moment I attach a load to it, it will stretch from this point to this point. I'm going to be taking from the center of gravity of this guy. So it's going to stretch from this point to this point. And this stretching here, we call it X, or the extension that has been produced in that spring. Now, if I add more load, for example, I add more load to this, what we will notice is another degree of stretching. So let's say I add two more to that guy, what you will notice is this. You see, our guy has stretched further from here again to about this point, or let's take it from this base. We take it from this base, we'll take it from this other base here. Exactly. And this will be X. If this is extension 1 or new length 1, no, extension 1 or, yes, it's just extension. Extension 1, this will be extension 2 or E2. Exactly. Change in length 2, yes, change in length or extension E2. Exactly. So you can see that our load caused this spring to elast, to increase in its original length. Exactly. So that extension produced is due to a load that has been placed on it. That load has caused it to undergo deformation. So this change that has happened to our spring here is called deformation. Deformation. Now, the elasticity of this material is what will now cause it to, after removing this load, this guy will now go back to being like this. Exactly. After you have removed this load, this guy will go back. It will return to its original position. So we say the body of this material is actually elastic. Exactly, it's elastic. Now, in 1600, in the 1660 rather, that's 17th century. In the 17th century, a certain scientist in 1660, that was his first mention of the law, of this is law, in a Latin anagram. His name was a physicist. He goes by the name Robert Hooke, or that was his name. So he, propounded a law that, explains how things get deformed and their response to that deformation. Okay, so what does that law say? Hooke's law states that the force applied on an elastic material is directly proportional to the extension produced, provided that the proportionality limit of the material is not exceeded. I go again, that the force applied on an elastic material, so this load applied, the force applied on an elastic material is very proportional. Sorry, there are two loads here. There are two loads here. When I added one, it stretched. Okay, it didn't stretch at all. Okay, I just showed the stretching here. Okay. So the force applied on an elastic material is directly proportional to the extension produced. provided that the elastic limit or proportionality limit of this material is not exceeded. What that means is this, that the elasticity produced in this material will be directly proportional to the increase in the force or load that is deforming it. As the load keeps deforming it, the extension produced will be proportional to the amount of load that is being added to it. What that means is, if I add 1 Newton to it, for example, it will stretch by 1 centimeter. If I add another 1 Newton, making 2 Newtons now, it will now stretch by 2 centimeters. If I add 3 Newtons, stretch by 3 centimeters. Do you understand now? So the extension produced is directly proportional to the force that is applied to its deformation. Do you understand? The force that is stressing it, the force is proportional to the extension that it produces, provided though that the elastic limit or proportionality limit of this guy, of this material, this elastic material, the proportionality limit is not exceeded. I'm going to, before the end of the video, I'm going to show you the biological implication of that law. Now, this therefore means that we need to show the, what's it called now? The constant of proportionality. So F therefore will be equal to KE. Is that clear? KE or KX. I like to use E because when we are dealing with this thing, simple harmonic motion, I prefer to use X for an object that is undergoing simple harmonic motion, okay? But I like to use E to show extension here because we're dealing with the force and the extension. So E represents extension well. All right, now, but the actual way to write this formula is not like this. Why? The correct way is actually F equal to minus KE. Now, what is the use of that minus? The reason for the minus is that it shows that the extension, the what's it called now? The material always goes back. The restoring force is always in is always opposite the direction. You know, it has undergone elasticity now. By the time I remove the load, it always goes back to its original position or its original shape, and we put a negative sign to show that it is always against the direction of the deforming force. Do you understand now? The guy gets to be restored by the in a negative direction to the direction to which it was pulled or it was deformed. Do you understand now? So that's the correct way to write the distance, the formula. But it doesn't necessarily affect our equation now. Now there's an implication with Hooke's law, and that implication is based on the diagram I'm going to show you now, which is the graph of Hooke's law. But don't forget, it was propounded by I think it was a British physicist in 1660, Robert Hooke, and he said that the force applied is directly proportional to the extension produced, provided that the elasticity limit is not exceeded. Now look at the implication of that thing. If you say that the elasticity limit is not exceeded, then it means that something will happen if the elasticity limit is actually exceeded, meaning that Hooke's law will not hold if elasticity limit is exceeded. So I'm going to plot a graph of force against extension, or you plot extension against force. It's pretty much the same. Depending on the material, the way they will react will vary. Is that clear? So, but for an elastic spring like this is pretty much what we're going to see. That this guy is going to undergo extension that is linearly proportional to the force that is acting on it. Meaning that as the force is increasing, the extension as well is increasing. Is that clear? For some materials, like glass materials, they can extend to this point, they will stop. Why? Because they don't have what is called plasticity. They don't have plastic property. I'm going to explain what that is. But for materials like this spring, for example, or the rubber band that we normally use to hold stuffs, this guy is going to still continue if you keep applying force. So as you keep applying force, our guy will begin to now, it will still continue to get a point here, it will still continue like this, then like this. Now there are various points on this graph I would like you to know. There is this point here, there is another point here, there is another point here, and there is this point here. Now let's call this point, let's call it ABC. A, B, C, and D. Now point A is called the elastic limit of the material. Point A, this point here, point A is called the elastic limit of the material. Now, what does that mean? It is the limit beyond which, listen now, it is the limit beyond which we are going to solve questions. I have about 5 exam questions that I've written down that we're going to solve. So stick with me till the end. I just want you to understand. The elastic limit is the point beyond which Hooke's law is no longer obeyed. What that means is, you remember Hooke's law says that provided that the elastic limit is not exceeded. So once this elastic limit is exceeded, any force applied will not produce a proportionate extension. That is, if you are now applying, if before, by the time you apply 2 more Newton of force, it will double the amount of extension. Once this elastic limit has been exceeded, if you add 2 more Newton, it will not double, but either maybe just produce 1 unit of extension or triple the unit of extension depending on the material. That one is depending on the material. But the point is that after the elastic limit, Hooke's law is no longer obeyed. Is that clear? After the elastic limit, Hooke's law is no longer obeyed. Okay? So now, then point B is called the yield point. The point of yieldedness. It has another name, I've forgotten. Now that point, that yield point, is the point where the body now becomes plastic. So that body begins to show plastic, beyond which the body shows plastic property. So it is beyond this point that the body shows what? Plastic characteristics. What's the characteristic of plastic? This is it. It is the yield point that begins the point where if you continue to apply force to this guy, that body cannot return to its original position again. Keep in mind, if you elast it to this point, the body will still return to the original position. You keep applying force to return to the original position. Keep in mind that this is from the original position of the guy. This is actually, we normally sometimes plot this guy from maybe from here to show that there is already an original length. But I'm starting from this point here to show that because it just force an extension I'm plotting is not with length. Is that clear? So the force applied, once you apply force, it will be as you keep applying the force, extension will keep extending and extending, but to a point where after which it cannot respond proportionately to the amount of force you are applying. But this yield point is the point where if you keep applying force beyond that yield point, that guy cannot return to its original position. Instead, it will take on the new shape. So this is it. If you ever use the rubber band to hold books together, a pack of books together, for example, look at this pack of books together that are here rather. If I hold them together with a rubber band for a long time, if you leave it for a while, for a long period, what you will notice is that that rubber band will take on that shape. Okay, it has become plastic, and it has become plasticized. That plasticization is that it has been stretched beyond its yield point, so it has taken on the shape of that position, that new position. It can no longer return to its original shape. Exactly. So it has become plastic in property. Okay, it will now take on the new shape. It will not be as elastic as it was before also, and it cannot go back to the original position. Then this point here is called the breaking point. Okay, breaking point or fracture point. So it is called the breaking point. Point C is the breaking point. Now, the breaking point is the point beyond which, if you still apply force, the guy shatters. The material does what? Breaks or shatters. Is that clear? So that is the breaking point. So these are the major points on this graph that you have to know, that you need to know. All right. So like I said, materials like copper, steel, they show this plastic property that I talked about. So, but materials like glass, ceramics, they don't show the plastic property. Once they get here, they stop. They will last to the point. Once they get to the elastic limit, they stop. They will break if you apply more force because they don't show plastic property. All right. So that's that about this graph. Make sure that you really understand this graph. Now, if I keep applying, let's now go back to our equation. Now, if I keep applying uh, if I apply force to something, that that force is going to act upon an area. So if I apply force over a cross-sectional area of a particular wire, for example, it is going to have a property known as stress. Okay, that property, the property of what I just did to it is called stress. And for a wire like that, it is called a tensile stress. A tensile stress, or compressive for materials that are, if I apply it over an area, exactly, the flat material, for example, that will be compressive stress. But I'm applying it over a length, the length of the material, like I'm talking about like a material that is like a wire, a string, exactly a string. So that is called tensile stress, from the word tension, exactly, tensile stress. Now, tensile stress is given by the force applied per unit cross-sectional area of the wire, exactly, or of the string. So that is tensile stress. It's given by F over A. That therefore means that, and keep in mind that it has the same unit as pressure, but it's not exactly pressure. Why? Because pressure is the perpendicular force over an area. Exactly, but this one is not necessarily perpendicular. If I'm talking about, if I'm stretching this thing, this is not perpendicular. But if anything, this is parallel to the direction of motion of that object. So if I'm stretching it, we feel force over an area, but the point is that they have the same unit. Exactly. The unit of force is Newton, the unit of area is meter squared. So it is Newton per meter squared. So the way you see it in exam is which of these has the same unit as pressure, and that is tensile stress. The next one is tensile strain. Tensile strain is now, depending on the amount of force over the unit area applied, what is the magnitude of the extension per unit of the length of the material. So that one is called the tensile strain. The tensile strain. There's no compressive strain, it's just tensile strain we have. Now, strain is the ratio of the extension produced over the length per unit length of the body. The extension produced per unit length, extension over length of the material. So, and it has no unit because the unit of this guy is meter, extension is meter, unit of this guy is meter, so meter cancels meter. Exactly. Then now for units too. You see, if you are given any particular unit, if other units correspond to are in the same unit as the unit you are given, that is different from meters, you don't need to convert. But we are giving unit in meters, for example, maybe you are giving what is called Young's modulus in meters, and you are giving other units in centimeters, then you need to convert. Or you are giving other units, other metric units, you need to convert back to meter. Now there is now the ratio of this extension, this stress over strain is called the elastic modulus, specifically attributed to someone called Young. So we call it the Young's modulus. Now Young's modulus is given by the stress over strain. That is the ratio of stress over strain. So it's given by that. They I didn't even talk about this K. I'll talk about this K in a jiffy. Now the formula will now become, let me clean this point. Make sure you are putting the notes, the penning down. Now, Young's modulus becomes stress, which is force over area, divided by extension over length, that is strain. So this becomes force over area divided by E over L. So force over area times L over E, right? That's Young's modulus. It's given by gamma, exactly. So gamma becomes, you must also see it as E, exactly. So that whichever one I decide to that is used in the convention, your textbook convention, you understand that it's the same. FL over AE. Exactly. So that's the formula for Young's modulus. where F is the force or load that is causing the deformation, the L is the original length of the material, A is the cross-sectional area over which the force is applied, and the extension is the extension that is produced, the increase in length or change in length. So this is the formula for Young's modulus. We're going to solve questions in a jiffy. Now there's now something else that you must know, and that is called energy stored in that string. Energy stored in the elastic string or in the spring. First, keep in mind that K is called the spring constant. This K is called the spring constant, or the elastic constant of the elastic string. Is that clear? So spring constant or the elastic constant of the string that is elastic. Is that clear? Because they are inelastic or inextensible strings. Okay, keep that in mind. Now the energy stored. How do we calculate energy stored? Now we think in terms of work done, because work done and energy have the same unit. So we think in terms of work done. What's work done? Work done will be the average force times the extension that is produced. That is just force times distance. You know that here. So what is average force here? Average force is going to be that. Average force is going to be from zero force, no force applied, to new force that is applied. So there are two forces. So that will be zero force plus the new force applied over 2 times the extension that is produced. Therefore, the work done or energy stored becomes 1 over 2 Fe. This is equation 1 for energy stored. The second equation you need to know for energy stored is, since we said that F is equal to Ke, I'm going to clean this back now. Since we said that F is equal to Ke, then we substitute into that equation, then W becomes 1 over 2 Ke times the extension. That becomes half Ke squared. Exactly, this is another equation for energy stored in the string. Look at where I derived it. Average force times the extension. That is force times distance. Average force, because why are we taking average force? Because we might apply different, when we begin to stretch, we might apply different forces, okay, different amount of forces, so we'll take the average of those forces. Is that clear? In this case, we are taking from nothing to the maximum force applied. That is 0, so it becomes 0 to the new force applied. That is, and there are two things there. So this plus this, to take the average divided by 2, 10 times the extension. So that's that for the energy stored. We are soon going to apply those formulas. Now, let's now look at the last equation that we need before we start solving questions. And that is the relationship between the extension of the material or expansion of the material due to change in temperature now. Okay, the expansion or contraction of material due to change in temperature. You will remember that we said that linear expansivity of a material is the change in length over length times change in temperature. Do you remember this formula? So in this case, we are going to say that linear expansivity is, keep in mind we are looking at expansion, okay? We are looking at expansion, okay, or contraction due to heat now, all right? So by the time we do that, change in length is our extension now over normal length and change in temperature, meaning that extension is equal to what? Alpha L delta theta. So we are going to bring in this into our equation. Remember that we said, so recall that, let's call this equation 2, let's call this one equation 3, given that I did not number the equations before. So from equation 3, we said that gamma is FL over AE, all right? It means that extension, which is this, will give us that gamma, Young modulus, is FL over A times, what's the extension now? Alpha L delta theta. Exactly. This is one equation. Then again, you can also have that make E subject here. If you make E subject here, E becomes FL over gamma A. Gamma A. Is that clear? Then an extension is already this guy, right? Therefore, we can say that extension being alpha L delta theta. Let's call delta theta. Let's call it temperature T. It's not confusing, is it? Delta theta. Maybe it's my handwriting there. FL over gamma A. Is that clear? So from here, we know that if we divide both sides by L will take care of L. Make sense? So alpha delta theta is equal to F over gamma A. Then if we divide through by this, alpha becomes F over gamma A delta theta. Exactly, that's another equation 4. So these are just the different. Now, this one shows the relationship between the elastic nature of the material itself and when it is not under when it is also under the influence of heat. Exactly. So these equations show their relationship. Now let's go on to solving questions. Make sure that you have copied all these equations down. Alright, let's attempt the following questions. The first one says a spiral spring extends by 5 centimeters. A spiral spring, question 1, extends. So write the extension is 5 centimeters. Now, I will check if I have to convert by checking my options. If my options are in centimeter, provided I'm asked, okay, I just need, since I'm not asked to calculate anything about length, it says we calculate weight. But the second extension is also given in centimeter. So I don't need to convert. Exactly. Since the two extensions are given in the same unit. So extension 1 is 5 centimeter. Keep in mind, extends by, that is the value of the extension. But I say extends to 5 centimeter, it means it's extended from one length to a new length. It means the new length is this 5 centimeter. But extends by means the extension is 5 centimeters. Under a load, so the first load or F1, so to speak, F1 is what? 60 Newton. When the load is replaced by a steel block, so the load is replaced by a steel block, the new extension, we now produce a new extension, E2 is 7 centimeters, 7 cm. The weight of the steel block is what? So we have to find F2 is what? Is that clear? Now, how do we go about this? Remember that we said that F is equal to KE, meaning that K is equal to F over E, right? So, I've showed you this in my other video on machines and the other guy. So, K equal to F over E, meaning that the ratio of, for a particular elastic material that has the same elastic, what do I call this guy? Spring constant or elastic constant. For that property, the load to the extension, the ratio of the force to the extension will be constant, meaning that F1 over E1 will be equal to F2 over E2 will be equal to F3 over E3 up to any number of F's and extension, in as much as we are dealing with the same guy that has the same elastic spring constant. So here, F1 therefore over E1, you know how I got this, right? Divided through by E. I divide both sides by E, and I have this. So F1 over E1 will be equal to F2 over E2. So what is our F1 here? F1 here is 60 over E1 is 5 centimeters. Is equal to F2, which is what we're looking for. F2 over, what is E2 here? E2 is giving us 7 centimeters. So by the time you cross multiply, you have 5F2 is equal to 60 by 7. Divide both sides by 5. This takes care of this. 5 here, 1, 5 here, 12. And F2 will be equal to 12 times 7, 84. 84 newtons. And that is the answer to question 1. What about question 2? With a mass of 25 grams, again we check, do we need to convert to kilograms? If we look at the other values, if it's still in gram, for example, it's still in gram, so we don't need to convert. So we say with a mass of 25 grams, so M1 is 25 grams. Then for those of you that those units and those parameters normally confuse, just stick with me and you're going to see the way I'll solve it. With a mass of 25 grams hung from its end, comma, the total length of the spring is 15 centimeters. It means the total length, let's call the original length, let's call it L0. But L1 be the new length when this one was hung. So that total length is L1, which is 15 centimeters. So we don't know the original length yet, and we don't know if that's what we're looking for. When the mass is increased to 40 grams, so that is, we made the gram to become 40 grams, that is, M2 is now 40 grams. The total length of the spring is 18 centimeters. That is, the length 2 is what? 18 centimeters. I hope you understand what I mean. It's very simple. Now look at what we'll do. You know, our equation says force over extension, force over extension. Then you now say, what about mass in this case? You know that weight is a force, right? So weight is mass times acceleration due to gravity. But I'll teach you one thing. You don't need to multiply by the acceleration due to gravity. Why? Because you are giving mass. So acceleration due to gravity will cancel out. As in, if you say it is weight 1, which is force 1, over E1, is equal to weight 2, which is force 2, over E2. Then you are saying that mass 1 times acceleration due to gravity. This acceleration due to gravity is the same here and here. So it's not 1 and 2. Do you understand? So it will cancel out. So for that reason, we don't need acceleration due to gravity. Hence, we can use our masses directly. So in this case, we are saying that 25 over E1. Now, what is our extension here? Normally, extension is the change in length, right? Now, what is change in length? L2 minus L1, or L1 in this case, minus L0. Does that make sense? Extension, the first extension now will be L1 minus L0, and the second extension, E2, will be L2 minus L0. Is it clear? L2 minus L0. Then some of you that might be confused to saying that, since they said that it was increased, should we just subtract the load and now get the new force? You will just be complicating things, because in that case, you still need here to subtract. It's not L0 you'll be subtracting, it's L1 you'll be subtracting from L2 now to get the extension. So it makes the equation, you are complicating matters. All you need to do is place your masses that have been given. So the first mass over the first extension produced is going to be L1 minus L0. That will be L1 minus L0 is equal to the second mass given is 40 over second extension L2 minus L0. Thank God we have L2, we have L1, so we can easily say that it is 25 over L1, which is 15, minus L0. Is that clear? Let's call L0, let's call it X. But before then, let's first write this. L2 is 18 minus L0. So let's call L0 X. So I'm going to change this to X, change this to X. I like to work with X, exactly. So I tell you cross multiply. I mean, from here, you can even divide here by 5. You have 5, divide here by 5, you have 8. To make what you want to do easier to do. So you cross multiply 8 into bracket 15 minus X is equal to 5 into bracket 18 minus X. Is that clear? For those of you that don't understand what I did there, if you multiply here, it's still 40 times this, and here 25 times this. 8, you can divide both sides by 5. So you still get this and this. Is it correct? Now, do we open the bracket directly here? Yes. Since nothing can really divide through yet. So we open the bracket. 8 times 15. 4 times 15 is 60 times 2, 120. So we have 120 minus 8x is equal to 5 times 180, 10 is 180, 90 minus 5x. So this guy comes here, we have 120 minus 90 is equal to minus 5x plus 8x. Let me show you something. See, as a student, you have to be very good and strive to be better than your master, than your teacher. So sometimes some of us teachers show some things and you might not understand. Ask your teacher the way he is doing it, because you, in your exam, you have limited time. So you need to upscale that skill, so such that you become even faster than your teacher. You know how to do it better than your teacher. If you agree, put in the comment section, I agree. That's what I'm saying. So this minus this is 30 is equal to, plus this minus this is 3x. Divide both sides by 3 and x equals 10. X is equal to 10 centimeters. Now what is that x? What are we asked to find? The unstretched length. So the unstretched length is the original length. So the original length is what? 10 centimeters. Now we'll go to question 3. Question 3. Question 3 says that an elastic string stretches to a total length of 3 centimeters, 30 centimeters rather. So the elastic string reaches this length. So L1, let's call it L1. Original length to be L0 now, exactly. So it stretches to this, which is 30 centimeters, under a load of 500 Newton. So F1 is 500 Newton. These are very simple questions. With an additional load of 100 Newton, so it means that the new force, F2 is now what? F2 is now what? Is 100 Newton plus this, which is what? 600 Newton. Do you agree? Because there's with an additional load of 100 Newton. The string stretches by a further 2 centimeters. It says further 2 centimeters. What that means is that the length that it got to before extended by 2 centimeters again. So L2 will have what? L2 will have what? 32 centimeters. Is that clear? This is the way I did it. So it now says the natural length, that's the original length. So we're looking for L0 again. That's what we're looking for again. Now, how do you find L0? You know that F1, the same method we use, F1 over, let me just leave you to solve this. Just do F1 over L1 minus L0, the same approach, exactly. You do that and put your answer in the comment section. Then I'll go to the next one. So it's very simple. That's why I'm not solving this. We've done something like that before. A spring of length 20 centimeters. So this one, we are giving the original length of the spring to be 20 centimeters. Stretches under a load of 50 Newton. The F0 applied, the F0, that is the, okay, it stretches, so F1, sorry. It stretches under a load of 50 Newton. That's 50 Newton. The strain in the spring is what? The strain in the spring is what? And we're not giving any other information. I don't know if that question is complete. In fact, I don't think it's complete. Of length 20 centimeter stretches by 7 millimeters. Stretches, so what is here is this, stretches by 7 millimeters. So it's not complete. So the extension has been given. The extension is 7 millimeters. Then it now says the strain in the string is what? What's the strain in the string? What's the formula for strain? Strain is basically the extension of our what? Length. So you see, don't let this guy fool you. You don't need the force for anything at all. So strain is equal to, extension here is in millimeter, length is in centimeters. So what you want to try and do is You can convert both to the unit you know, which is meter, or convert this one back to centimeter. You'll get the same answer. But I like to do it to meters. So convert this one to meters, divide by 100, give you 0.2, right? So from millimeter to meter is dividing by 1000, right? So that will be 0.007, 7 over 1000. Alright, so meters. So our strain, therefore, strain, stress is given by the stress is denoted by this, just in case I didn't mention it. Stress is denoted by this, and strain is denoted by, so this is sigma. Strain is denoted by, I've forgotten. So strain will be extension, which is 0.07 over 0.2. To solve this is very simple. Just do like this. 1, 2, 3. Then move this guy to 3 times. 1, 2, 3. So here, the point has come forward, meaning this is now 7 over 200. All you need to do is this. 2 here, 100. 2 here, 3.5. Make sense? So you now go divide by 100 again. 1, 2. So the answer will be 0.035. No unit. That is the strain in the string. Is that clear? So there are many more questions here. This will be for this video. Let me solve this last question. This one says a wire of cross-sectional area 6. Maybe I should write it here. Let me just solve it. You can write the question down. It says a wire of cross-sectional area, maybe I should show you so that you can see it. A wire of cross-sectional area of 6 times 10 to the power minus 5 meters squared. So the area is given as 6 times 10 to the power minus 5 meters squared, and the length is 15 meters. So area is 6 times 10 to the power minus 5 meters squared, and length is 50 centimeters. So keep in mind that you must what? Convert here. Stretches by the extension. When you hear stretches by or extends by, you have been given the extension. You are not given new length or anything. It is the extension that you have been given directly. Stretches by 0.2 millimeter under a load, that is force now, a load or force of 300 Newton. The Young's modulus. Calculate Young's modulus. It's very simple. Recall that Young's modulus, which we don't know, that's what we're looking for, is FL over AE, right? What is the force? The force is given. The length, we need to convert everything, all these guys to meter, because this area is given in meter squared. So to convert this one to meter, divide by 100, right? Divide by 100, you have 0.5 now, because it's 1 over 2, 0.5. Then this one, 0 meters. This one divided by 1000 to give 0.0002 meters. Let's do that. 0.2 over 1000, 1, 2, 3, 1, 2, 3. 0.0002. Alright, so our answer becomes 300 times the length, which is 0.5, over the area, which is 6 times 0 times 10 to the power minus 5, times the extension, which is 0.002. Alright, from here we can easily do our manipulations. 3 can go here 2, 3 here 1, 100, 2 here 1, 2 here 50. Is that correct? Then 2 here 1 also, 2 here 25. So we have 25 times 0.5 here. 5 times 25 is 125. So 5 times 0.5 will be 12.5. Exactly. So 12.5 was 1 times 10 to the power minus 5. So this is just times 10 to the power minus 5 times 10 to the power here is minus 3. So minus 3. Why is it minus? Because this is minus 3, but division gives it this first minus. Exactly. So this becomes 12.5 times 10 to the power 5 plus 3. So the answer is 12.5 times 10 to the power 8, which is in standard from 1.25 times times 10 to the power 9. What's the unit of Young modulus? It's the same as unit of stress, as Newton meter per meter squared. So that will be the answer. Do well to subscribe to the channel. God bless you as you subscribe. God bless you. And share the video with your friends. And take the channel to 1 million subscribers. God bless you.